Welcome back, everybody. It's very heavy on this side of the room. This side of the room is a little sparse tonight, but that happens. You know, just like charges, you can move around, right? Yeah, right. Maybe there's an electric potential in the room.
Or maybe there's positive.
Oh, is this the positive side of the room or the negative side of the room?
Positive.
This is positive? You said you don't know, so maybe you're neutral because you're along the midline.
Yeah.
Pretty negative. Sure. Kind of wrong. So, welcome back. It was pretty nasty out on the road, so I imagine some people are going to miss it. It was tough. I drove in from Edinburgh. I was sideways a few times, but I've been here long enough. That's just normal. Yeah. So you guys are important, and I was going to make it. If I had to walk, I was going to make it. All right? Not to be denied. So we talked last time just about the class, and we talked a little bit about charge and what charge means. We didn't really talk about where it comes from, but we started to, because I put a number up on the board. Do you remember what that number was?
1.602.
Oh, I didn't. It was a second class. They told me to write it down on the board, so I didn't see it. 1.602 times 10 to the negative 19. Negative 19. Positive 19 would be a really big number. It's actually a really small number. Well, that's where we're going to start today. We're going to start off talking about that today. So if you didn't get it last time, you get it this time.
Just a random question. Do you like have like a PowerPoint?
So yeah, if you go on Blackboard, I didn't give you a tour of Blackboard last time. I don't know why I didn't. But Blackboard is set up so it's divided by chapters that we cover. And if you click on that chapter, the textbook PowerPoint that is aligned with the lessons. I don't like using PowerPoint. I feel it's a little bit constrictive for me or restrictive for me. But I know that you guys like having that as a resource, so I put it up there for you. It's the same PowerPoint I would use if I was lecturing from a document.
So for your notes, is it mostly just like you lecturing, or are you using like the whiteboard?
Yeah, both.
Both, okay.
Yep. But the whiteboard's a little hard to see because those whiteboards suck. So I'm probably going to present off my iPad.
Oh, yeah, okay.
If that works for you. So when I'm solving problems, I try to put them up there. But I also do the whiteboard sometimes. I actually like the chalkboard more, but it gets messy too. So I don't know. It's on a whim, but I try to be consistent. I fail, but I try. Yeah.
Like the little links that you have, like the little YouTube links on each unit, are we like supposed to watch those for like the exams too, or is that just like extra?
I don't think I'm going to test you on any of those things.
Yeah.
If it's not something I cover in class, or at least talk about in class, then I'm not going to put it on the exam.
Okay.
That's stuff that is interesting connections. It's the same stuff. So at the end of the day, that stuff is the same stuff that I'm teaching. It's just applied to a specific scenario. So like I think I put something about electric fields and bumblebees or honeybees. I'm not going to test you about honeybees, but it's the same thing conceptually. So if you understand that, you'll understand this stuff too.
I think for Physics 1 for the homework help, you have those videos
I
post.
I made those on demand. Because like, if I got the same question 2 or 3 times about a homework problem, I would just make a guide video about how to do it, just to save myself responding to emails. So I can do that from time to time as needed.
And then for the homework, I don't know if anyone else, but like we both couldn't figure it out, that we bought like the whole semester. We can't figure out how to log in.
Dr. Jones emailed me yesterday, and it was about this. So thank you for the reminder. I'm going to call up the email, and I'm going to read it out loud to you, because she knows more about this software than I do. I'm sorry, it's not my fault. Don't let it reflect my evaluation. So she said, hi, Dr. Johnson. Grace came to see me today asking for help, and this is what I found out. Any student who purchased a 2-term version of WebAssign will need to call the following phone number. I'll write that on the board. The agent will then map their purchase to the new course. They said there's no way to do it automatically, which makes sense because they don't want the university's versions 1 and 2. They don't know what the versions 1 and 2 of the course are, but they should not pay any more money. Just call, and the mapping is instant. Just wanted you to know. All right, so I'm going to put the phone number on the board. We'll put the phone number on this board over here. If you can't read it, it says 800-354-9706. If you bought both semesters, call them, they'll fix it for you. If you didn't buy both semesters, I guess you just buy one semester.
I know once they fixed it for me, it still said like I had a free trial and it was expiring, but they said to ignore like that pop-up. So it's like there's still a banner that says free trial expiring soon, just ignore it.
I don't know, I've never used this before. It seems like a little bit cumbersome, but what are you gonna do? Oh, sign in sheet. Anybody not sign in? This half the room? You guys signed in? Everybody got it? Everyone's, okay. If at some time, like, you don't get the sign-in sheet, and you know that I did pass it out, just make sure you sign in before you leave, that's all. We'll get used to each other. Okay, you ready to start? Do a little bit of physics? Okay. Any other questions before we do get started? All right. Remind me that number again? The one I told you at the end of last class?
The 1.02.
I've got all the individual numbers right, but I don't know if you got them in the right order.
1.6 times 10 to the negative 19. Oh, what did I say? Oh, wait, I do have 1.6. That's my bad.
1.602 times 10 to the negative 19th. That's a really tiny number. What are we talking about? 1.602 times 10 to the minus 19th what? You said charge,
KP.
and it is measured in coulombs, capital C, coulomb. Named after a guy named Charles de Coulomb. He studied electrostatics, I think, in the 1700s. I'm not 100% sure on that. I think he was French. That's not particularly important. C-O-U-L-O-M-B, Coulomb. In fact, he's so important that we are going to talk about his law today, at least at the end. That was supposed to be today's lesson, but we're like half a day behind. So a coulomb is a certain amount of charge that is on an object. It's actually a really, really big amount of charge. If you have 1 coulomb of charge, you have a huge amount of charge. So we're going to be talking about coulombs in terms of like micro coulombs and nano coulombs. So everyday versions of charge are fairly small. 1 coulomb is a big number for perspective. All right, cool. Now, what does this number represent? It's an amount of charge, but the amount of charge on what? On what?
A proton.
On a proton. That is exactly right. How do I know it's a proton and not the other one?
It's positive.
Because it's a positive number. That's exactly right as well. Good job. Dr. Treat's good with you guys. All right, so what this tells me is that charge comes in little increments. And those increments are the charge on the individual particles that carry the charge around. The things that carry the charge around are protons and electrons. And they both, as it turns out, happen to have the exact same amount of charge, just one is a positive type and the other is a negative type. Electrons have negative charge, and that's just by convention. I mean, it has a certain amount of charge, and that charge we call negative. Protons have the exact same amount of charge, and we call that positive, because they're different, they're opposite. We need to differentiate them somehow. Positive charges, protons. Negative charges, electrons. And charge, we say in physics, is quantized, which means they only come in discrete packets. It's like money is kind of quantized. You can't get any lower increments than a penny, right? If I give you a penny, if I give you 10 pennies, or I give you 100 pennies, or a million pennies, I can't give you like half a penny if I'm dealing in actual hard currency cash. So it's quantized because it can only be discrete. It can only go in increments of 1 cent, $0.01. Charge is the same way. It only goes in increments of this. If I want to charge an atom, I'll either take away one of its electrons or I'll give it an electron, and it gets a net charge of either positive or negative, that. When I'm charging up an object, I'm either giving it a bunch of electrons, and it has an amount of charge that is some integer multiple of this, or I'm taking away electrons and giving it a charge that is an integer multiple of this as well. Every single time I take electrons from you, I'm making you more positive, I'm making me more negative. Does that make sense to you? Every time I give you my electrons, I'm making you more negative, I'm making me more positive. If you have an atom and you take one of its electrons away, it's a +1 charged ion. If you give it an extra electron, it's a -1 charge. It's quantized, it comes in discrete packets, but that packet is really tiny, 10 to the -19. So we don't often really see that quantization if we're dealing in everyday life, if we're dealing in a regular scale, like the normal scale that we deal in just as we're going about our business. If you're dealing with individual atoms, then yeah, the quantization is important. Make sense? So chemistry class, important. But most of the time, if we're like making a circuit or we're charging a battery or something like that, those numbers are going to be really big and the increments are really, really tiny. So you don't see the steps. It looks like a smooth curve. Does that make sense? All right, cool. So how do we move electrons around? We talked, one of my classes talked about this. I don't remember if it was you guys or the next one. But how do charges get moved around? Say what? Forces can move charges, yeah. And those forces can come from a variety of different places. So if I have two charges near each other, they're going to apply a force to each other. If they're both positive, what kind of force are they going to feel? They're going to repel each other. Like charges repel, you've heard this before. If they're opposite charges, or if they're both negative, same thing. So those are both like. If it's both positive, both negative, they get pushed apart. And that can move charges around. We're going to talk about that today when we talk about charging by induction. If we have opposite charges, they're going to attract each other. If I have a proton over here and an electron over there, they're going to get pulled towards each other. You're going to feel an attractive force, just like gravity. Does that all make sense to you? Nice. Okay, cool. So I can move charges around without even touching them. It's like magic. I did it with the magic wand last time. I was moving the foam balls around a little bit. I can also move charges around through direct contact. You've seen this before. I know my grandpa used to do this, so I thought it was like the coolest thing. I'm not doing it. I need help though, because I don't have enough hair for this experiment. Are you game?
I guess.
All right. So if I have a material that has a high electron affinity, that's the word. Sorry, I was mixing up my vocabulary. Large electron affinity. It wants electrons. If this balloon has a higher electron affinity than her hair, then if I put them in direct contact, some of the electrons from her hair are going to stick to the balloon. Now, the balloon is made out of latex, which is an insulator, an electrical insulator. It's important that we differentiate because there's thermal insulators and there's electrical insulators. This is an electrical insulator, which means it holds onto its electrons pretty tightly. That means electrons don't move around on the surface of this very easily. They can. I can put electrons on it and I can pull electrons off, but they don't spread out. They don't move around.
That's with all insulators, right? Not just, okay.
Another term that we use for insulator is dielectric. Your book might use that term. We're going to use that term when we talk about capacitors in the not too distant future. So they're synonyms. Insulator and dielectric mean the same thing. It's just a material that doesn't let the electrons move around very much. The opposite of an insulator is,
Conductor.
you know, what's the opposite of an insulator?
Conductor.
A conductor. Like, anybody play music? Conductors? Different kind. But ride a train? Also, not the same thing. Conductors are materials that let their electrons move around. Electrons are free to move. Metals tend to be electrons. When you have a bunch of metal atoms together, the electrons are kind of like this soup of electrons that are free to move throughout the structure of the material. And as such, they're easy to move from place to place. That's why we use metals for our wires, to transfer electrical energy from place to place. So, as I was saying, insulator, so if I do put charge on it, that charge is going to stay where I put it, which is kind of nice, because it's easier to control that way. So, I take the thing that wants the electrons, I put it next to a thing that has some extra electrons, and through friction, I connect the two. Now, that spot right here has extra electrons. It's negatively charged. Her hair has less electrons, so notice they feel an attractive force towards each other. Can you see it? Moving there, isn't that cool? I can stick it to the wall too. We'll talk about that in a minute. In case you guys over here didn't see one. Volunteer? Volunteer? Who's? Okay, ready? You can move the air around. it's an attractive force because they're oppositely charged. I would try it on my head, it just doesn't work. Actually, I'm going to try something. All right, so I just charged this up. I'm going to hold that like this. It's already feeling an attractive force. I'm going to charge this up. I want to find out if this is positive or negative. Where was the spot I charged? Rub that on your head so I know where. Is it pulled towards it or away? Oh, it's towards, definitely towards. So if that's negatively charged, then this is too. We just learned something. That's kind of neat. I just learned something. Didn't know that was going to be the case. That is charging something through direct contact or through friction. We are actually physically touching the things together, pulling electrons off, and putting them onto something else. The fact that it is an insulator means the electrons stay in that one spot, which is convenient for our little experiment we did. If this was not an insulator, and it was like a tin foil balloon where it's got a metallic sheeting on the outside, and therefore was a conductor, what would happen to the charges that I put on it? I said that since it's an insulator, they stay put right there. If I put a bunch of negative charges right here, do they want to be near each other? Thank you. They're like stinky roommates. You want to spread out as much as you possibly can, right? You want to get as far away as you can, occupying as much space as you can. So if this was a conductor, not an insulator, what would happen to the charges that I placed at that spot right there? They wouldn't stay in that spot. Where would they go?
Everywhere else.
They would spread out all over, as far apart as they could be. How could they spread out as far as they could be from each other? They would occupy evenly distributed space on the surface of the balloon. So sometimes in the upper division class, we talk about charge distributions. We talk about charge per unit area. And the charge per unit area would become a minimum, because it would spread out as much as it could. As it is, it stays put because it can't move around. The electrons are held too tightly. Does that all make sense to you? All right, cool. So the effect of that is actually super cool. Have you ever heard of a Faraday cage? Some sci-fi movies make reference to Faraday cages. No? There's one, there was a show maybe 5 or 6 years ago where aliens came and I think it's called The Colony. And they colonize the city and people are like, no? Well, they used Faraday cages in that. I don't know. It was a good show. I think it only ran 1 season. That's a shame. Right? So what is a Faraday cage? A Faraday cage uses the concept I just talked to you about. The charge wants to spread out. If you have a conductor, the charge wants to spread out as much as it possibly can. So let's say I'm in a metal cage, like a bird cage, right? And if that bird cage gets struck by lightning, I could actually touch the inside of that metal and I wouldn't get zapped. Because the charges don't want to go to the inside. They want to stay on the outside so they can be as far apart from each other as they can. Now I might get cooked because there's heat given off when charge moves through a metal. That's how old school incandescent light bulbs work. They would heat up a filament until it got so hot that it would glow. That being said, I wouldn't get zapped. It's the same reason why if your car gets struck by lightning, you don't get zapped. You, again, could get cooked, but you won't get zapped. People think it's because of the rubber tires. Now think about this. Air is an insulator. Air is a electrical insulator. And that lightning bolt just went through miles of an electrical insulator. Do you think a couple inches of another insulator are going to make a big difference? No, not at all. So it's not the rubber tires that protect you, it's the metal frame of the car. It's called the skin effect or a Faraday cage. Isn't that cool? I think it is. If you ever have a chance to go to Boston, in Boston they have a science center, and in the science center they have something called a Van de Graaff generator. We have one in the lab. It's the metal sphere on top of the pole. We'll play with it either in lab or in class sometime. They're super cool. You touch them, it makes your hair stand up. It's very high voltage but low current, so it doesn't hurt you. In Boston, in the Science Center, they have a 2-story tall one that was made by Van de Graaff himself because he taught at MIT. And during the show, they have a lightning show. They have a guy standing literally in a human-sized bird cage who's controlling the Van de Graaff. It shoots 10-foot bolts of lightning through the air. And the guy actually has it strike the cage he's in, and he touches the cage while it's striking lightning on the other side. And it doesn't zap him because he's in a Faraday cage, because of the skin effect of the conducting surface that he's inside of. It protects him. Isn't that cool? It also protects from other types of signals. That's why sci-fi uses Faraday cages. You can put a cell phone in and the signal doesn't get out for similar reasons. Isn't that cool? Come on, that's cool, right? Okay. All right. I think it is. Yesterday in lab, did you guys do the name that charge simulation?
Yeah.
All right. Did you all finish it?
Yeah.
I was thinking about doing a few of them, but if you already did all of it, like, it won't help you, right? You already did. But we're going to talk about that stuff. We were supposed to talk about it the day before lab, so it would have been easy, but you didn't get a chance to. You weren't here Monday. That's neither here nor there. So in that simulation, you have to start thinking about the thing we're thinking about right now, how electrons behave inside of conductors, how they behave inside of insulators, and how they move around because of that behavior. If I charge my balloon up, it's charged, it's negatively charged, and imagine, if you will, that this is not a piece of plastic, but imagine it's a piece of metal. Imagine this is like an iron rod. I bring my negatively charged balloon near that metal rod. What happens to the metal rod? The electrons in the metal rod, it's a conductor, so the electrons aren't held very tightly, so they can move all over the place. They just go where they want to go. There's an excess set of electrons on here. It's negatively charged. Do the electrons in this rod want to be near those electrons? No, so where are they going to go? As far away as they can be, right? They're going to be pushed away until what we're going to learn is the electric potential equates, until it's even, until it equals out. We reach an equilibrium. So they're going to go to the other side. Hold that. Good catch. The electrons get pushed away from the balloon to this side of the rod, which leaves this side with less electrons than it started with, right? So what would you say if you were describing this side of the rod to me? Positively charged, it has less electrons. How about this side over here? I have induced a charge in this rod. It's now a dipole. There's a pull on this side and a pull on that side. There are two poles, a dipole. Positive charge on one side, negative charge on the other side. All right, now if I move the balloon, I throw it and you catch it, it's nowhere nearby anymore. The electrons go back to where they were. We reach a new equilibrium. Because they don't want to be together over here, they're forced to be together. So they spread back out. And since it's a conductor, they evenly distribute throughout. Make sense? Okay, cool. Well, what if before, so I bring that balloon nearby, and before I pull it away, I take my ninja sword out, which I do own, and I go, and I cut it in half, and I pull them apart, separate them by a column of air. I told you air is an insulator, right? So this side was positively charged, and that side was negatively charged, and I separate them apart, right? So I end up with a chunk on this side that is and a chunk on this side that is negative. And they're stuck that way, right? Until I give that charge somewhere to go, it's stuck. It can't move. Unless I connect it to something that is conductive, it's going to be stuck. Yeah?
So when you touch the negatively charged balloon actually to that rod when it has protons, what happens to the charge of the balloon? Does it stay negative?
Oh, that's a great question. That's a great question. Let's talk about it. So, charge it up. It's just fun. I like seeing your reaction. And I actually put it in physical. The first time when I was describing it, I didn't touch it.
Yeah.
But now I do touch them. When they're in direct contact, the electrons can actually move, can't they? So this has extra electrons on it. They don't want to be there. They want somewhere to go, but they're stuck because it's an insulator and there's nowhere for them to go. But I touch a metal rod on it, it's a conductor, so they are going to spread out. They don't want to be near each other, and now they can move. Now you've given them somewhere to go. So they touch together, and the electrons, the excess electrons from this are going to spread out onto this. Yeah?
So maybe it's but are all of those conductors neutral?
Everything starts off neutral, unless you're told otherwise. Your normal atoms that exist in the universe are neutral. When I'm walking through the world, I try to go towards neutrality, not like actively, consciously, but that's the, what's the right word I'm looking for? Things want to be neutral, because if I'm positively charged, I'm going to pull electrons onto me until I'm neutral. If I'm negatively charged, I'm going to be giving up electrons at every opportunity until I'm neutral. Neutral is where, like, the ground state, the most stable place to be. Things in nature try to seek out the most stable orientation for themselves.
Did you say when the balloon and the rod touched that the electrons would go from the balloon to the rod?
If this is negatively charged and this is neutral, the negative charges want somewhere to go. right? So when I touch them, it gives them somewhere to go, and they're gonna spread out as much as they can. So the negative charges are gonna be pushing each other apart in, when you touch it and give it somewhere to go, they're gonna push them onto that rod, which gives the rod a negative charge. It's gonna continue taking on negative charges until those charges equate, because then they're gonna be pushing the same side on both sides. Because once I've negatively charged this, the electrons don't wanna be together there either. They're being forced into that position. But once the charges are equal on both sides, then the push on this is the same as the push from this.
So
So
the rod would be negative and then the balloon, what would?
Still also negative, just a
Okay.
little bit less negative than it was.
Okay.
You ever notice that when you get out of a car in the wintertime and you touch the gas pump, you get zapped? You will now. Do you drive? I guarantee you get out of your car today, it's going to zap you. And it's happened a bunch of times, you just never have noticed. But now I pointed it out, you'll notice. And have you guys, other than me, noticed that? How about in the wintertime when you're getting dressed and you take one shirt off, put on another shirt, that shirt gets all staticky, right? How come? The lack of humidity in the wintertime, that's why it happens in the wintertime and not really very often in the summertime. This shirt is super sticky to me right now because it's very low humidity right now. Humidity increases the conductivity of the air. So in the wintertime, very low humidity. So when I get out of my car, my clothes rub on the seat. And the same way that when I do this, it moves electrons, the same thing happens to my clothes in the car seat. So I become charged. It happens in my office all the time. Every time I touch my office door, it zaps me. Yeah.
Yesterday in lab when we were trying to put the charge on the
Yeah.
it was snowing.
Mhm.
So we couldn't
Interesting.
And the Dr. Tree said it was because of
The humidity.
because of the snow.
Interesting. It seems like that would help you, but I don't know. I guess snow is water and it is in the air. I don't know. I wouldn't argue with Dr. Trees. He's pretty smart.
Yes, it was a good.
Just a couple. But I wouldn't argue with him about those things. Really good questions. Did I answer the question, the initial question about the balloon?
Yeah.
Okay, cool. Did I answer the other questions that were subsequent? All right, awesome. I want to make sure that I didn't leave any. Sometimes we go from topic to topic and I never fully answer the one question. So I want to make sure that I do. Saw people looking at the clock. You got somewhere to be?
Me?
Looking over at the clock. I'm teasing you. That's just me jokes.
So how would you know when the balloon is neutral again? Because you were saying it gives the electrons that's just slightly less negative.
Yeah.
How would you know when
It's a really, really good question, and one that isn't easy to answer. So we know things based on our observations of how it interacts with other charges. Electrostatics describes interactions of charges when they're not moving around, and that's what we're in right now. So we would need to look at how it reacts to other things. I actually don't know if it's positively charged or negatively charged unless I go look up the electronegativity and know how it got that charge and know where those charges came from. So the behavior really isn't any different. If I have two positive charges or two negative charges, they're going to repel, and I don't know whether they're positive or negative. That's why Ben Franklin guessed wrong when he guessed what was moving, because there is no way to tell the difference. They behave exactly the same. If this was positive and this was negative, they'd attract. If this was negative and this was positive, they'd attract, and you wouldn't really be able to tell the difference. But if I charge something up and I bring it near and it doesn't really react to this, then this thing must be neutral, right? Because I know this is charged and this doesn't react. But if it gets repelled, I know it has an opposite charge. If it gets attracted, I know it has an opposite charge as well. Oh wait, if it gets repelled, it's the same charge. If it gets, yeah. I said it wrong because I was excited. I apologize. Listen to her, not me. Did I fixed my
Yeah, I
mistake?
think that makes sense.
Alright.
So how do they figure out which one was positive, which one the electrons moved then, if you can't tell?
So, I hate to say it, but we work with people like chemists who deal with electrons. Other physicists do experiments where we know what's happening, right? We know things have certain electron activities and certain electron affinities, and we know that electrons are moving from one to the other, so we have a known value, and we see how it interacts with other stuff. We can create potential differences. And based on the conventions that we've established, we can identify what those potential differences are and what they would do to positive charges and what they would do to negative charges. We'll talk more about that when we get into electrodynamics. Yeah.
So I know in one of the name the charge things, like one of the examples was like you had the balloon, it was like negative or positive and it came close to the rod. And then the other side, you touched it with your hand. So then what would happen with like
What
the
a great
charges?
question. It leads right into what I was supposed to talk about next. So, awesome. So far, we have charged things through direct contact. I put negative charges on it, I touch it, they both become negative. This one's a little less negative, this one's more negative than it was. I charge it up, I bring it nearby, I don't touch them. It still polarizes this, right? And creates positive on one side, negative on the other side. But if I pull it away, it's gonna just go back to normal.
Yeah.
Well, what if I connected a wire to that other side and connected that to some place for charge to go? We usually call a place for charge to go the ground. You've heard of this, grounding a circuit? The ground is just a place that charges can go to or come from. It's this infinite well of space for charges to either go to or come from. So if I connected a wire to this side and connected that wire to the ground on the outlet, or just a big piece of metal, or the literal ground that I'm standing on, and those, that cable, that grounding cable, gives the electrons in here somewhere to go, or it can pull electrons from there indefinitely. So I bring my negative charge nearby, it pushes all the electrons to the other end, but they don't want to just stop there, they want to get as far from this as they can. So they're going to get driven down that wire and out to the ground, which leaves this whole thing
Positive?
positively charged.
Okay.
Now, I cut the wire, I pull this away, I have a positively charged rod.
Okay, and then the ground would be negative, because that's where the
Well, the
electrons.
ground is infinitely big. It
Yeah.
is neither negative nor positive. It's just a place for charges to go, or a place where I can get as many charges as I want.
Yeah, so like say your hand or something else touched it, like a can, then it would be negative, because the
Yes,
electrons are going
there you
forward. Okay.
Yeah, awesome.
When I wondered, like, if the balloon was completely negative and the rod was like neutral, why wouldn't the balloon then become positive? Like, why would it stay negative? Because I was wondering.
As a system, if I look at the whole system, if this is negative and this is neutral, I have an abundance, an excess of electrons. And those electrons can't disappear. This is another thing, so great question, because the last thing I was talking about in this section of the lesson is the conservation of charge. The charge can't be created, it can't be destroyed. Whatever total charge I have is the total charge I end up with. Unless I send it to some like other place, like the ground, a ground in a circuit that can absorb the excess charges. I don't build up charges in the middle of a circuit, and I don't just create charge out of nowhere. I can just move charges around. So I got a whole bunch of extra electrons, and I have a normal, like, even neutral distribution here. As a system, it has an overall negative charge. And those charges can't just disappear. So even though I'm spreading them out over both of the objects, it's still an overall negative charge.
Okay.
Does that make sense to you? Cool. And because of the behavior of the charges, I'm not going to be able to, unless I do something else, like with magnetic fields or electric fields, I'm not going to be able to push more off of this than an even distribution of charge across the field. Really, really good questions, because you're hitting on all the points that I wanted to talk about. So I appreciate it. Good job. If I had gold stars, you would have them. They would be yours. Any more? Going once, going twice. Sold. I mentioned a term. I said when half of this is positive and half of it is negative, what did I call that? A dipole. It's polarized, because there's two different poles. One side is positive, one side is negative. I think a dipole, if I'm getting exactly literal, is like one positive charge on one side, one negative charge on the other side, but it's polar, it's polarized. Atoms can be polarized. Atoms can be positive on one side and negative on the other. Because how do atoms connect when they're in molecules? I should have said molecules, not atoms, but molecules can be polar. Atoms, not really, because they got electrons spinning all around. But molecules can be polarized because when I connect atoms together to make molecules, how do I do that? How do they bond together? What holds atoms together in molecules?
Bonds.
What kind of bonds? What bonds together? What is it?
Electrons.
Electrons, right. So it's covalent, valence electrons, right? Or ionic bonds, ions, that's electrons too. It's the electrons that are holding things together. And like, let's take water, for example. You've got an oxygen, you stick a hydrogen to it. The electron on the hydrogen bonds with the electron, the empty space in the oxygen, and the electron in the other hydrogen, same thing. The only electron on that hydrogen is stuck to the oxygen, so what's left on the other side? Any electrons on the other side of that hydrogen atom? No, they used them all up to bond, right? So that leaves the proton side of the hydrogen atom exposed, leaving a positive side where the hydrogens are attached. It attaches like an upside down Mickey Mouse head, right? You've seen the diagram of that? It's got the, like a Mickey Mouse would be the oxygen and the two ears would be the hydrogens. You can imagine this? Okay. So where the two ears are, that's just exposed protons from the hydrogen. That's a positive side, right? The other side of the oxygen has a full valence shell now. So it's got an octet, 8 electrons around the outside, which means it's negative on the other side. So it's polar, right? So we've got a positive side and a negative side. And since it's polar, I should be able to affect it with other charges nearby. Let's see if we can do that. I am. You want me to pick on somebody else? So I have a bottle here. Inside the bottle is water. There's also one other thing inside this bottle, or I guess it's not inside the bottle, it's on the bottle. It's a hole. There's a hole in the bottle. If I squeeze the bottle, water comes out. The water doesn't come out because, we learned this last semester, part of it is surface tension, but it's also fluids will flow from high pressure to low pressure, but the pressure is equalized. So the outside atmospheric pressure is enough to hold that water in. But if I equalize the pressure on the outside and inside by opening the lid, then the pressure from the water pushing down will push the water out of the hole. So I open the lid and the water comes out, giving me a stream of water. Yeah? All right, so since I have a stream of water that is just going to flow based on gravity as a projectile, it's going to follow projectile motion, unless I do something to it. What I'm going to do is charge up my balloon and bring it near that stream of water. And if the water is in fact polarized like I thought, I should be able to deflect the stream of water towards the balloon. Make sense? Shall we try? You want to be my partner on this one? All right. So I'll need you to hold the bottle and open it up once I'm ready. And then we'll bring the balloon nearby and we'll see if it deflects the water. We'll go up there and do it again. All right, you ready? Whenever you're ready, open it up. You got to open. Okay, there it is. It's flowing through. Am I deflecting the beam? Mm-hmm. All right, put the lid back on. You did that on purpose. It does, in fact, deflect the beam. Isn't that cool? You want to be my bottle person? You want to be my hair electron bank?
Sure.
All right, cool. Ready? Here we go. All right, go ahead. Open it up. Deflect the beam. Can you see it deflecting? Oh, that was a good one. Look at that. All right, put the lid back. You guys see it okay back there? Please? No, yeah? You guys see it okay? I can come over there and do it again. It's not that hard. Okay, let's do it again. They want to see it one more time. One more time. Only there was no way to fix it. All right, we're good. Open up. I want to spit it away from you. And deflecting. I can't even see it. Is it deflecting? Yeah. I don't think I got a good charge, but it's deflected a little. I think we could probably do better if we want to try again.
Do it again.
Right? Am I getting charged? It's not charging up as good as it was. I think some of the water splattered onto the balloons, which is leading the charge off into the water. So we'll try one more time. I'm going to try the other side of the balloon. Maybe that'll be better. Just because I like torturing students. All right, go ahead. That one's better?
No.
Yeah, okay, good. All right, you believe me if nothing else.
That was pretty cool.
I'm not touching it on my home. Although I think I reviewed. I'm not sure.
Yeah, but she didn't.
I'm going to check my notes real quick to make sure I'm not forgetting anything. We still got about 5 minutes. I want to introduce Coulomb's law. I just want to make sure I didn't miss anything in the first half. Positive, negative, positive is.
That wasn't
All right. Darkness insulator.
Yeah.
Awesome. Okay. Good job, team, because we covered everything that I had highlighted in my notes that I wanted to cover for the first half. We are not done because we're going to talk about Coulomb's law. So far, we've been talking about things in terms of generalities, right? We've been talking about what a charge does, kind of just in general. It'll be repelled. It'll be attracted. It'll just stay stationary. But we haven't quantified it at all. We haven't talked about how much. And we know that in physics class we quantify everything that we can. So we want some way to calculate exactly how much it's going to get pushed away, or exactly how much it's going to get pulled towards. And Coulomb's law is our way to do that. Do you guys recall Newton's law for gravitation, universal gravitation? If I have two pieces of mass that are existent in space, you can calculate how much force is between them. Any two pieces of mass. It could be a planet and a star. It could be two planets. It could be two stars. It could be a black hole and a planet. It could be me and a planet. It could be an asteroid and another asteroid. It could be your iPad and the floor. It could be your iPad and me. Any two things that have mass feel a gravitational attractive force towards each other, and I can calculate it using Newton's universal gravitation. Do you remember that equation? F sub g equals capital G. You don't know? I'm going to write it on. That's no excuse. Oh, Dr. Jones, yes, right? I guarantee she at least mentioned this to you at some point. Now, the good thing is for this equation is that most of the time you're on the surface of the Earth. So my distance from the middle of the Earth to me is pretty much fixed. It's a constant, so that R value is a constant. And the mass of the Earth is pretty much fixed. It's not getting much bigger or smaller. So it's also a constant. And the capital G is the universal gravitational constant. Constant's right there in the name. It doesn't change. It's a constant. So since this one, and that one are all constant, I can make a single constant out of them, and that's lowercase g. So we have another equation for force of gravity. That one's probably more familiar to you. That lowercase g is just this constant, that constant, and this constant all put together. But it's only true for the surface of the Earth where those constants are what they are. The top one is more universal, hence the name, universal gravitational equation. Now, why am I talking to you about gravity? I thought we were talking about electricity. Well, as it turns out, Coulomb's law, which defines a similar quantity for electrical forces, is mathematically identical. The format mathematically is the same inverse square law as this. It's a constant multiplied by two scalar quantities divided by the distance between them squared. Except in Coulomb's law, since we're not talking about gravitation, we're talking about electrical forces, we're not dealing with masses. What do you think is going to take the place of the masses?
1.602.
Say what?
The 1.602.
Well, the charge.
Yeah.
So if I do have a proton and electron, that would be the charge. But if I have a whole bunch of electrons and a whole bunch of protons, then it's whatever the total charge is. So you're on the right track. Good job. So Coulomb's law says that the force between two charged particles, and it is a vector. I'm a little lazy about drawing my vector symbols sometimes, but force is a vector, is going to equal the Coulomb constant, K, times the product of the two charges, Q1 times Q2, divided by the distance between them, R, vector, squared. We also add one more label to this in the complete form. You put a little R with a hat on top next to it. Last semester, did you ever talk about what that little hat means on top of a symbol? Maybe, maybe not. It just means what direction it's going in. the little hat above a vector quantity like that says that's a directional vector. So what does that mean? It means that the force that you're finding, the force vector, will be in the direction of that line between them, the distance between them. So I have charged particle here, charged particle there. If I drew a straight line between them, the force is going to be on that line, either towards or away, depending on whether they're both positive, both negative, or one's positive and one's negative. They're either directly towards each other or directly away from each other along the radial line between them. I said a lot of words. Do all those words make sense in the order I put them in?
So the article hat, is that what you mean?
It's just a vector notation that tells you what direction it's going in.
Okay, so
When you're using your mathematical calculations, that doesn't necessarily play a role. It just tells you, because a vector can't be true and complete unless you know what direction it's going in. That tells you what direction it's going in.
Do we have to measure, like memorize all the equations
I give you an equation sheet.
and then the constants?
Yeah, same. If it's something you could look up easily, I'll tell it to you or provide it for you.
So what is this equation exactly telling you? Like,
It tells you how much force charged particles will feel due to other charged particles. You could say it's the electrostatic force. If I have two protons near each other, I have proton A and proton B. By the way, Monday's class, I was going to do an example, but I'm going to run out of time. Monday's class, we're going to start with an example where we calculate some of these.
So Fc is the force of the charge. R is,
The C is for Coulomb force.
okay. R is the distance. What is
The amount of charge. We're going to go piece by piece.
And then is K that number that we?
K is a constant. I haven't told you what K is yet,
Okay, that makes more sense.
but I'm glad you asked because I'm about to.
Okay.
I just want to make sure that the stuff I've said so far hasn't confused people yet. You good?
I was just scratching my head.
Oh, it's all right. My first class I ever taught at the college level, I had a student sit in the back of the room with his hand on the desk just like this. So I constantly was calling on him. It's like, no, I don't have a question. Don't sit like that. It's so distracting.
I bet.
All right, so let's talk about what each of these symbols means, and then we're going to be done for the day. Okay, I'm going to talk real fast. As I said, that's the electrostatic force. It's the amount of force that each particle is going to feel. Because of Newton's third law, we know that if one thing makes a force on the other, that thing is going to feel that amount of force too, right? If I push on the desk pushes back on me. So both charged particles are going to feel the same amount of force, just in opposite directions. K is the K constant. K equals 8.99 times 10 to the 9th, I think. Double check that for me.
Yeah.
I have it in my notes. I'm going to make Siri tell me. Yep, 10 to the 9th. Newton meter squared per Coulomb squared is the unit for it. I'm going to give you an equation that you don't need for a couple weeks, but you're going to write it down. I'm going to refer to it later. This comes from other constants. K equals 1 divided by 4 pi epsilon 0. That doesn't mean anything to you now, and it won't mean anything to you for a couple weeks. It will mean something to you in the future. So F is force, K is the constant. I just gave it to you. It comes from this. Q are the two charges that are feeling the forces. R is the distance between the two charges. That's all I've got for you today. Have a great weekend. Drive safe. Be careful. Behave. Have fun.